Welcome to this sailing theory tutorial. My name is Julian. The topic of this video is airflow over sails. And my goal of this video is to improve your understanding of how sails really work. And I want to do that by using terminology, diagrams, and scientific principles that are common in fluid dynamics. Now, airflow and aerodynamics is a very big topic. And because I'm trying to keep these videos under 30 minutes, this video will only provide a brief background on flow visualizations with Streamlines, and then we'll move on to showing the airflow and approximate pressure distributions for a properly trimmed sail. In a future video, I intend to cover improperly trimmed sails, including stalled sails, separation bubbles, luffing, and backwinding. And in yet another video, I'm going to present to you the topic of circulation. This video is going to cover what's happening as air flows around your sail, and the circulation video will probably help to explain a little bit of why that's happening. So in real life, sailboats exist in three dimensions. They have a height, a length, and a width. And it should come as no surprise that as wind flows around a sailboat, it's able to flow both up and down, left and right, and forward and backwards. The problem that we have is as we try to understand the airflow around a sail, tracking it in three dimensions can get very complicated very quickly, and it's going to be nearly impossible to draw by hand. The way we're going to solve that problem is we're going to take the boat and we're going to cast it down onto a coordinate system that looks from the top and from the side of the sailboat. And once we've done that, we're going to make a cut line through the center of the sail. And we're going to place our eyes at that cut line looking down. And what that gives us is what's called a section view. So the section view shows the sail at the same length as the cut line, and you can also see the deck of the sailboat. For the rest of this tutorial, we're going to be working with a two-dimensional flow approximation over the section that we just created. Believe it or not, this is still a technique that's used today by aeronautical engineers before they go on to solve the three-dimensional problem. We're talking about airflow, and what we're really trying to do is keep track of what the fluid velocity is at different points in space and time. One of the ways that we could do this is to create something that's called a vector field. And a vector field is a diagram with evenly spaced vectors throughout it that indicate the direction and magnitude of the flow at any point. For our very first airflow diagram, let's consider a wedge. The wedge is going to split the flow into two streams. One stream is going to pass below the wedge, and the other stream is going to pass above the wedge. The vector field has a couple of disadvantages though. One of the disadvantages is that there are a lot of small little vector arrows that we have to draw. And another disadvantage is it's not always going to be obvious to us what's going on in between the vector arrows. So this is where the concept of streamlines comes in. And a streamline is a line that traces the path of a particle as it moves through a flow. And we're going to see here that it's actually tangent or takes the direction of each vector arrow that it touches. We drew the streamlines in the last example with the help of the vector flow field arrows. In real life, though, we don't have a series of vectors to help us visualize the flow. So what we do in experiments is seed the flow with either a fog or a smoke so that we can see the particles moving through the flow. If we were to take a picture of a stream of smoke through a wind tunnel, what we would see is essentially a streamline. I want us to be able to draw our streamline diagrams without having the vector arrows there at all. And in order to do this, we need to know a couple of rules about streamlines first. The first rule that I want us to know is because particles can only have one velocity at any given point in space and time, streamlines don't intersect. What that means is they can get close to one another, and indeed they do sometimes, but they can never touch. The next rule that we need to learn has to do with conservation of mass. Remember that streamlines are representing the path of a particle, and that particle can't be destroyed. So if it enters a diagram, it has to exit the diagram as well. If the streamline comes in touch with an obstacle, it has to go around the obstacle. It can't just disappear. The third and final rule that I want to tell you about streamlines is that because of inertia, streamlines really don't like to take sharp corners. So when we're drawing a streamline, we're going to want to make sure that every turn that we take has a radius to it. What that means is that it's going to be round, not pointed. We've spoken a fair amount about representing the direction of velocity with streamlines. But remember that the other component of velocity that we need to represent is the actual speed of the fluid flow. So what we know is that a faster flow means that more particles will be passing through an area per unit time. As an example, I want you to think about a hairdryer on high speed versus low speed. If we were to draw a hairdryer on low speed, we would draw a certain number of streamlines coming out of the end of the hairdryer. If we drew that same hairdryer on high speed, with a higher speed flow coming out, to represent it accurately, we would have to draw more streamlines coming out of the nozzle. As a second example, I want to consider a nozzle. The job of a nozzle is to take a low speed flow and speed it up. If we draw streamlines through the nozzle, we'll see that as the flow is sped up through the nozzle, the streamlines get closer together. What we can take away from this is that on diagrams that have streamlines, in areas where the streamlines are locally closer together, we can expect that the flow is going to have a higher velocity. And in areas where the streamlines are locally spread farther apart, we can expect to see a relatively slower velocity. The idea of local changes in the speed of a flow, and locally faster and locally slower flows, leads us into Bernoulli's principle and local pressures as well. Bernoulli's principle tells us that along a streamline, as a flow accelerates, its pressure changes inversely with the change in velocity. Now what that means is that an increase in velocity will relate to a decrease in pressure, and vice versa. Looking back up to our nozzle diagram, what we would expect to see is a higher pressure on the slow side and a lower pressure on the fast side. And if we measured it, that's exactly what we would see. The last topic that we need to learn before we're ready to draw our airflow diagrams is the idea of stagnation. So what is stagnation? Stagnation is when the velocity of a fluid particle goes to zero as it approaches a boundary. To give you a sense of why stagnation is important and to show you how to represent it on a streamline diagram, I'm going to show you a couple examples. One of the most intuitive examples that I'm aware of for a stagnation streamline is the example of a wall perpendicular to the flow. So in the case of a perpendicular wall, what we're tasked to do is extend these streamlines from the entrance of our diagram to the exit. The first streamline that I want to consider is this center streamline right here. It's not obvious to me whether this streamline should go over the top side of the wall or over the bottom side of the wall. And in fact, what is obvious is that we don't have any information to help us make that decision. The truth is that this streamline doesn't pass on either side of the wall, but in fact it continues straight up to the wall, just like this. Now this streamline is a special streamline. It's called a stagnation streamline. And when it reaches the wall, it has a velocity that's equal to zero. And what it also means for us, based on our Bernoulli's principle, is that because we have a relatively low velocity, we would expect to have a region of high pressure. Now we can move on to the other streamlines. So this streamline over here would continue parallel to the stagnation streamline for a while. But one thing we know about high pressure regions is that the streamlines are spread apart locally. So what we would expect is as we get closer and closer to the high pressure location, our streamlines are going to spread farther and farther apart until we get to the wall
where we would expect that this streamline is going to be running parallel to the wall, because it's never going to intersect the wall. The next streamline is going to do something very similar, and it's going to take a gradual bend away until also it runs parallel to the wall. On the bottom side, because of symmetry, we can expect to see the exact same thing. We bend away from the high pressure zone that exists next to the stagnation streamline. So now I think we actually have enough background information to start drawing an airflow diagram around a sail. Remember that we said that this is a properly trimmed sail, and so what that's going to tell us is that we're not going to have any flow separation off of the sail, and we'll assume that the flow adheres to the sail all the way around. We're also going to assume that our streamline diagram is big enough that the top streamline and the bottom streamline are basically unaffected by the sail. And so I'm just going to connect them from one end of the page to the other in a straight line. The next thing that we need to do is identify where the stagnation streamline is going to come from. Now, we really don't have enough information to make a scientific determination of where the stagnation streamline is going to come from, but in general, in airflow around an airfoil, it's going to come from somewhere below the airfoil. So either this one or this one would be a good candidate to be our stagnation streamline. In this case, I'm going to pick this one right here. And what you'll see is I'm going to connect it as a dotted line up towards the leading edge of the airfoil. So that's our stagnation streamline. Now, so that we can obey our rule about every streamline entering and exiting the diagram, we're going to draw another stagnation streamline that comes off the trailing edge of the airfoil. And what we want it to do is come off the trailing edge and return back down to the same height that the stagnation streamline entered. Now we have a landscape set up to draw the rest of our streamlines. I'm going to fill in the streamlines below the airfoil first. Notice here that we have a lot of space that's opened up between the sail and the bottom streamline here. And what we're going to expect is that these streamlines are going to evenly disperse in that space so that we have the streamlines spread farther apart. That's the streamlines below the sail. Now let's work on the streamlines above the sail. So this streamline right here, directly above the sail, is going to follow along, and as it gets closer to the stagnation streamline, the higher pressure of the stagnation streamline is going to push it up. It's going to push it up and around the back side of the sail, until it eventually comes back out at the same height that it came in. The line right above it is going to follow a very similar path, and it's going to get close, and then eventually it'll spread back out to where it was before. And we'll follow the same pattern all the way around the sail. Two more to go. And what you can see is that as we get up towards the top streamline, we're getting affected less and less. So this is essentially the airflow diagram that we expect to see around a single sail sailboat. A couple of interesting things to point out are areas on the top side of the sail where the streamlines are spaced close together, which indicates an increased velocity, and it also indicates a decreased pressure. On the bottom side of the sail, we see the exact opposite. The streamlines are spread farther apart. And what that means for us is that we have a decreased velocity, which corresponds to an increase in pressure. So to show you that I'm not completely making this stuff up, I've installed an app called Wind Tunnel on my tablet. This app is really just a bit of a toy program, but you'll see that some of the features that we talked about in our diagram before will appear in this app as well. The first thing I'm going to do is draw a sail in the flow. And now I'm going to slow the flow down a little bit to make a more realistic picture of what's going on. Now, let's ignore the waviness, because this app is simulating smoke, which we know would disperse a little bit in a real wind. If I freeze the frame, I'm going to trace the streamlines. So what I want to do is trace the streamlines in this diagram, which is a screenshot from the app we were using, and compare them to what we came up with above. The first thing that we notice is that there's a lot of swirls and waviness in this diagram down here. We're going to ignore that because we don't know enough right now to tell what's going on with turbulent flow. The app is simulating smoke in a wind tunnel, and like I said, it's a bit of a toy app. So we're not even sure whether these swirls are something that would really be happening or if it's just something that the app is adding to be cute. So the first thing we notice is that the stagnation streamline starts from below the sail and curves up towards the leading edge of the sail, like we said. We can see that mass leaks around the top side of the sail like this, and this mass is what we would expect to eventually form the stagnation streamline that comes off the trailing edge of the sail and bends back in the direction that it came in. Like we said in the picture above, the streamlines at the very top and the very bottom of the wind tunnel we can expect are far enough away that they're not affected by the sail, and so we would draw them as straight lines. The streamlines below the sail, just like we drew before, spread out to fill the space that's formed between the sail and the bottom streamline. Above the sail, we have a similar picture again to what we had above. The streamline directly above the stagnation streamline is going to bend up around the top side of the sail, come down until it eventually straightens out behind the sail. Each streamline above that is affected slightly less and less as we get farther away from the sail, but they have a characteristic bend that follows the shape of the sail. So if we compare these two diagrams, we see that they share very similar features. Notably, we see a low velocity, high pressure area below the sail, and we also see a high velocity, low pressure area above the sail. And these are all of the important elements that we need to show in our airflow diagrams when we're talking about airflow around a sail. So up to this point, we've just been identifying regions where we have low and high pressure. But what I want to do now is get a little bit more into detail about what pressure is and how it acts on the sail. I think that this will go a long way to explaining how sails actually work. So if we were to graph the pressure as it acts along the sail, we could draw it as little arrows. What I'm going to do is use yellow arrows for low pressure, and I'll use pink arrows for high pressure. So on the top surface of the airfoil, we would expect to see not very much pressure acting at the very front of the airfoil. But as we get into this region here, where we have the streamlines spaced closest together, the pressure arrows are going to get bigger and bigger until we reach a peak. And right after that peak, they're going to sharply fall off as the streamlines spread farther and farther apart. On the high pressure side of the airfoil, we would expect to see somewhat the same thing. As we get into the widest part of the spread apart streamlines, we will have the most pressure acting. And then later, as the streamlines come closer together, the distribution is going to get smaller and smaller again. Something that we need to know about pressure is that it has dimensions of force over area. And so what we can think of then is that each of these little pressure area arrows that I've drawn is an infinitesimal force acting along the area of the sail. And if we add them all up together, what we end up with is one resultant force. And I'm going to draw it here in red. Now that resultant force is fine, but in aerodynamics we often talk about two very special forces, and one of them is called the lift force. And the lift force always acts in a special direction, which is perpendicular to the oncoming flow. The other special force that we talk about is the drag force, and the drag force acts in the direction along the flow. So what we can do is break this resultant force up into the lift and drag forces. And these are the forces that actually describe how the wind acts on our sails. This concludes my sailing theory tutorial on airflow over properly trimmed sails, and how your sails really work. I hope in this video the background that I provided helps you understand what's going on in the diagram. I've shown you how to draw an airfoil diagram over a properly trimmed sail and talked a little bit about the pressure distribution over a sail. In a future video, I'm going to talk about sail trim and improperly trimmed sails, and we're going to use the same diagramming techniques. In yet a third video, I'm going to introduce the topic of circulation. Circulation explains, among other things, why the stagnation streamline comes from below the sail instead of straight on like this. And it also really explains why sails generate lift at all. Thank you for watching.